So we were discussing pulse propagation in a dispersive Kerr nonlinear medium. Right, so basically we have some medium which has a nonlinearity, effective nonlinearity gamma, and some dispersion, specifically, let's say some amount of beta 2 or GVD, but in general could have higher orders of dispersion also. Right, so this gamma was related to the nonlinearity, third order nonlinearity, N2, the nonlinear refractive index coefficient, and this dispersion could have higher orders also. And if we launch a pulse in such a medium, last time we derived an equation to see how this pulse will propagate in the medium, right? So let's recall we had derived this nonlinear envelope equation, right? So basically we wrote it like this. So the amplitude or the envelope of the pulse A, right, as a function of the position and this retarded time tau, which is in the frame of the pulse, right? So as the pulse propagates, that is the propagation direction here. You saw that it gets modified due to two terms, right? One is dispersion and one is nonlinearity. So the first term is the dispersive term. Right, so this D was the dispersion operator given by, so in general it goes from the second order to all as many orders of dispersion you want to consider, right? So beta n over n factorial and nth derivative with respect to time. Right, and then the nonlinear term was of course proportional to the nonlinearity gamma. Right, and then it went as mod of A square A, which is basically self-phase modulation. Right? So yeah, right. So you can clearly see that the pulse envelope is modified by two terms. One is dispersion and one is nonlinearity. Right. So today we'll look at sort of the manifestations of this equation, right, and take certain limits where we can simplify this equation further and neglect some terms respect to the other, depending on which parameter regime we are working in, and we'll see different kinds of solutions. Okay, so right, so this was basically self-phase modulation, and this term we briefly mentioned last time is called steepening, because it results in a steepening of the trailing edge of the pulse. Okay, so this is basically the full-blown equation that you can use to analyze any pulse in any medium. But typically, we can simplify this further. Okay, by making certain approximations. Like, so the first is if the So if the pulse duration, the optical pulse duration is some tau p, right? And if tau p is basically greater than, much greater than 1 over omega naught. So so omega naught is the center frequency or the carrier frequency of the pulse, right? So remember, right? So last time we took the electric field as this amplitude A. So A is the envelope, right? Times this carrier, which goes as omega naught t. So the oscillations of the carrier within the pulse are going at a frequency omega naught. So the time period here, so the cycle time is of course proportional to 1 over omega naught, right? So, and this tau p is the total pulse width. So what this is saying is that if your pulse contains many cycles, right, then if you have such a case, then this self-steepening term, which goes as 1 over omega naught d over d tau, okay, that is small, right? So this 1 plus the derivative with respect to time we can neglect, right? So if this is the case, so basically optical pulse is very long compared to the optical cycle right? So if your pulse is very long, which means it contains many oscillations, typically let's say hundreds to thousands of oscillations here, then basically we can say that so this term 1 over omega naught d over d tau, right? You can see that that will so d over d tau is sort of the slope, right? And that will go sort of as 1 over tau, right? So this will be of the order of so this derivative term will be order of 1 over the pulse width, right? Because that's the slope. So if I have a longer pulse width, then this will be smaller, right? And so by this approximation, so 1 over omega naught tau p will be much less than 1, which means we can neglect the self-steepening.
Sir, how is slope equal to 1 upon tau p?
Sorry?
How is slope equal to 1 upon tau p?
Yeah, so I mean, in the most crude approximation, let's say you approximate this by a straight line, right? Then basically you have the d over d tau will basically be the amplitude divided by the pulse duration, right? So, but even if for a different pulse shape, the point is that it will be of the order of 1 over tau p. Maybe it will go as some other power of tau p or something, but still sort of order of magnitude, it will scale with tau p, right? So if I increase tau p, of course the derivative goes down, right? So that's sort of, we are not saying that it exactly goes as 1 over tau p, but it scales with tau p inversely, roughly, right? So yeah, we're just saying order of magnitude. If this is very small, then the derivative term will be much smaller than 1, and we can sort of safely neglect, right? And this is true. So typically, right? So 1 over omega naught is a few femtoseconds. So Typically, if you take the wavelength in the visible or infrared, so let's say if you're working from 500 nanometer to let's say 2 micron in that range, then the cycle time will be a few femtoseconds, so roughly like 1 to 10 femtoseconds. Okay, but typically the pulse widths that usually we consider are more than at least 100 femtoseconds. Okay, so for if you have a 100 femtosecond pulse, then you have at least 10 to 100 cycles, depending on the wavelength within your pulse. And for longer pulses, picoseconds and longer, then you have thousands of these cycles within the pulse. So this is a very good approximation for this. If you go down to very short pulses, like less than 50 femtoseconds or right close to 10 femtoseconds, then you can't neglect this term, right? So for really ultra short pulses, which are also called few cycle pulses, right? So if you look at the field, it will actually, for those pulses, it will look like this, where actually it consists of only a few cycles. Okay, so in that case, yeah, this term is not negligible, and you have to consider the self-steeping. But for most practical cases, we consider pulse widths more than 100 femtoseconds, and we can neglect the self-steeping. Okay. Also for these fairly long, I mean these are still very short, but long compared to the cycle time. So this dispersion operator has all orders of dispersion, right? But again, if you have more than 100 femtoseconds or picosecond pulses, typically the n equal to 2 term is much bigger than the higher order term. So we only keep the GVD term, the beta 2, and neglect all higher orders of dispersion. Again, if you go to shorter pulses, 50 femtoseconds or smaller, then you have to. And in some other cases, if the bandwidth is too big, right? So another way to write this condition is that omega naught is much greater than 1 over tau p, right? And if you recall, 1 over tau p was proportional to the bandwidth of the pulse, right? So remember, if we had a pulse in time, we take Fourier transform, we got a again sort of a pulse in frequency, and we had a bandwidth, right? So this bandwidth, that omega in frequency, was proportional to 1 over tau p, right? Where tau p is the width in time. So this 1 over tau p is basically proportional to bandwidth. So here we are saying that the carrier frequency omega naught is much bigger than the bandwidth, right? So the center frequency here, omega naught, is much bigger than the bandwidth, right? So that would be what is called a narrow band pulse, right? Because the spread in frequency is much smaller than the center frequency. Okay, and dispersion, you know, is basically different frequencies are traveling at different speeds, right? And because of that, the different frequencies acquire different phase, and the pulse broadens as it propagates, right? Now, if the spread in frequencies is small, then only the first order term is majorly contributing, right? And the higher order terms, because we did the Taylor expansion, right, by definition are small. But in case you had a very broadband pulse where the bandwidth becomes comparable to the center frequency, then basically you have to take the higher order terms also. Okay. Or in some other special cases, for example, if you're working with some special medium where beta 2 is actually close to 0. Let's say you're working, so you get, for example, optical fibers, where at certain wavelengths, the GVD goes to 0, right? So let's say if you're operating there, then of course beta 2 is 0, so you have to consider the next higher order term, beta 3. Okay. So apart from those kinds of cases, either a very broad bandwidth pulse or very ultra short pulse in time, or if you're working near 0 GVD, basically only the first beta 2 GVD term contributes and the others are small. Okay. So again, in most cases, we can neglect n greater than 2 terms. Okay, so if we make those two approximations, right? So here we drop the derivative term, and d we only keep the beta 2 term. So then we get a much simplified equation. Okay, so again, so in the case where the pulse width is much longer compared to cycle time, or the carrier frequency is much bigger than the bandwidth in the pulse, basically this nonlinear envelope equation reduces to okay. So the dispersive term just has beta 2 now, and the second derivative with respect to time, because the n equal to 2 term, and here we get rid of the self steepening and we have only the self phase modulation, gamma mod a square. Okay. Okay, and this thing is called the nonlinear Schrodinger equation. Okay, can you see why it's called the nonlinear Schrodinger equation? Does it seem familiar to the Schrodinger equation? Right. So what is Schrodinger equation? If I write so if I write a one-dimensional Schrodinger equation, then I have a term del psi by del t. Then I have a second derivative del square psi by del x square, and then some potential multiplied by the wave function. Right. So here this term corresponds to this. So A, the envelope of the pulse, is something like analogous to the wave function. The propagation direction z is something analogous to time in the Schrodinger equation. This retarded time in the frame of the pulse tau is like the spatial coordinate in the Schrodinger equation, and this thing multiplying A is like the potential V. Okay, so the potential here is again itself proportional to the pulse amplitude, right? So the potential itself goes as mod a square or the intensity in the pulse. So that's why it's called a nonlinear Schrodinger equation. Right? So it looks like a Schrodinger equation with the potential which is nonlinear. So it's called a nonlinear Schrodinger. This kind of equation occurs elsewhere in physics also, not just in nonlinear optics. So that's why the general form is called nonlinear Schrodinger equation. Okay, so for most cases, I would say maybe 90% of the cases, one can analyze using the NLSE, pulse propagation in current nonlinear medium. You can just use NLSE. Okay. For a very small minority of the cases, right, where again, as I said, the pulse width is really small, consisting of very few cycles, or bandwidth becomes really large, or if you're operating at some special points in the material, you have to consider this. But for most cases, NLSE is more than sufficient. Okay, so let's look at the solutions to this NLSE in different limits, okay, to see how basically the pulse changes, right? So first, simplest case is, let's say the medium has no dispersion, no nonlinearity. It's a linear medium with no dispersion, like, I don't know, air, free space, let's say. So in that case, basically this term is 0 and this term both are 0. So then basically the equation is just del A by del Z equal to 0. So there is no change in the pulse as it propagates. So the pulse which is launched at Z equal to 0 remains the same as it propagates. Okay, no change in that. The simplest. So, I mean, of course, we expect this, but yeah, it also just double checks that the equation makes sense. So, second case. So, no nonlinearity, but so only dispersion. In other words, a linear dispersive medium. Right. So, for example, it could be the same medium, but the intensity is low enough such that the nonlinear term is negligible. So, for example, when we do optical communications, right, fiber optic communications, on which basically we build the internet, right? So we send these pulses across long distances, and there we make sure that the pulse energy is small enough such that we are in this region, okay? Such that nonlinear effects are negligible, and only thing you have to consider is dispersion. Okay, so then the equation, you just neglect the second term, the nonlinear term. Okay, so we can actually get analytical solutions to this equation. So how do we do that? So you can convert this again to the frequency domain. Okay, so to take the Fourier transform, which is, we go to this omega space, remember? So this capital omega is the detuning from the center frequency, omega naught. Right. So we take the Fourier transform. Then, so this is derivative with respect to z, so that remains like that, except now we have a of omega. Here we have a double derivative with time, right? So if we take double derivative with time, we get again 2 factors of this omega in front, right? So we get an omega square. So this becomes okay. So now this equation is very simple to solve, right? I have dA by dz equal to some constant times A, right? So I know how it's a straightforward solution. Right, so the solution is that A at Z is the input A at 0 right? This, so the solution is just e to the this term, right? Z. So you can see that what is dispersion doing is basically adding a phase which is frequency dependent, and to be more specific, it's adding a phase which is quadratic in the frequency omega square, right? And basically this is the effect of different frequencies traveling at different speeds and requiring different phases, right? So the different frequencies, we are adding a phase which is frequency dependent, and you can see this beta 2 omega square is basically coming from, so remember we expanded the beta as beta naught plus beta 1 omega plus beta 2 omega square, right? So this beta 2 omega square is basically the effect of that, right? So you can imagine if you include higher order terms, you just have the higher order terms coming here, beta 3 omega cube plus etc. Okay. And one other thing to note is if I take the mod square, so the intensity remains the same, there is no change, right? It's only a phase. So the power spectrum is unchanged. So this is a solution in frequency, right? But of course, we're interested in how the pulse looks in time. So then we have to take an inverse Fourier transform. So take the inverse Fourier transform, which is basically go back to A of tau right? So, and for Az of omega, you put this, right? So here, the integral that you get is basically, so A of 0 we can take outside. Outside. A of 0 is a function of frequency, so that remains inside. Right, so the integral we have here is Okay, so we have e to the I some quadratic function in omega, right? And we integrate over omega. So this integral is called a Fresnel integral. So this form appears in other places in optics also. Like for example, if you consider a beam which is diffracting in space, if you want to see how the diffraction pattern looks, then this integral, basically the same integral shows up there. Right? That's why it's called the Fresnel integral. Okay, so basically solve this integral and that's the solution. Now, of course, we need a at 0, z equal to 0, which is the input pulse, right? So we need to assume some input pulse. So let's assume that the input pulse is Gaussian in time. Right? Which means that a at z equal to 0 or a of tau is some a naught e to the minus tau square by 2 tau naught square. Right? So if you plot the pulse in time, right? So if you plot the power, which is mod a square, as a function of time, you can see square of this. So this p naught e to the minus t square by tau naught square. Right? So this pulse width here is related to tau naught. So specifically tau p, which is the full width at half maximum, if you want to take from half p naught by 2 p naught by 2. The tau p is related to this tau naught like by this factor. So about 1.6 times tau naught. Okay, basically, so tau naught is some constant which is determining the width of the pulse. Right, and P naught, the peak power here is mod a square. Right? This P naught at tau equal to 0. Right? So tau equal to 0 is the center of the pulse. Right? So remember we had normalized A such that mod a square gives me power. Okay, so that's my input pulse. So if we have such a pulse in time, then basically first we need to find what is the spectrum A0 of omega. Right? The input pulse, the frequency spectrum. So we need to take a Fourier transform of this input pulse in time. Right, so A 0 comma omega is basically, so this A naught right, so Fourier transform of my input pulse. And this integral also has an analytical solution. Okay. It's basically like an integral of a Gaussian function, right? Except you have this extra sort of linear term here, but okay. So the integral solution. So basically, there's an integral formula. So these types of integrals, which is okay. So it's a generalization of the Gaussian integral with a linear term. Okay. So a and b here could be complex numbers, right? In this case, b is a complex number, right? But this formula holds for a, b complex numbers. Okay. So using this formula, we can solve this integral like that. So that gives me the spectrum. So you can see that spectrum is also Gaussian, right? It's e to the minus something omega square, and the width in the frequency domain is what? So the width in the time domain was given by this tau naught. Width in the frequency domain is 1 over tau naught, right? I can write it as omega by 1 over tau naught. So, of course, that is what we expect, right? So the spectrum of yeah.
So from the Fresnel integral, we can say that in a dispersive medium, the pulse width actually disperses, diffracts.
Yeah, so it's the same integral. So in the it's basically a temporal analog of the Fresnel diffraction integral. Okay, so in the spatial case, we know that a beam would diffract or spread. Similarly, here we'll see that in time, and the pulse will broaden in time.
Okay, sir.
Right, as it propagates. Yeah, it's the same thing. Right, so the spectrum is also Gaussian. Right, where this the spectral width here is proportional to 1 over tau. Right, so smaller the pulse, shorter the pulse, wider the band. Okay, so now we basically put this expression for the input spectrum into the Fresnel integral. Okay, so we start to write it out. Okay, so we get this integral now. And you can see that this integral is again of this form. Right? So ax square, so we have omega square with some coefficient here, and then a linear term omega some coefficient. Okay, so we can use the same integral formula to solve this also. So Yeah, before that we just sort of write it in a slightly different form. So beta 2 here, we write it as, so beta 2 we write as the sine of beta 2 times the magnitude of beta 2. Seems a weird thing to do, but we'll see why we're doing that, right? So we're just saying that the number is the sine times its magnitude, right? So if it's negative, then it's -1 times its magnitude. If it's positive, it's +1 times. Just right. So the sine function is +1 if this argument is positive, right? It's -1 if the argument is negative. So let's rewrite this integral. Okay, so we write this term like this now. So we took the sign and then introduce this parameter LD. What is LD? LD is equal to tau naught square divided by the magnitude of beta 2. Okay, and this is known as the dispersion length. Okay, so it's some characteristic length, we'll see, that over which the pulse spreads. Okay? So it's analogous to if you're familiar with the Rayleigh range or the diffraction length, right, for a beam which is spreading in free space. It's the analog of that. So it goes as the square of the temporal duration divided by the magnitude of the GVD. Anyway, so we have this integral now again, which is of the same form, right? So we use the same formula to solve this. We can write the solution again using this formula. We get okay. So the solution looks like this. It's still a Gaussian in time, right? Tau square by some constant. So this was my input pulse, a naught e to the minus p square by 2 tau naught square, and this is my pulse after propagation distance z. So you can see first of all, so the peak amplitude here was a naught, but now it's a naught by this factor. So the peak amplitude has gone down, and the pulse width in time initially was given by tau naught, but now it's tau naught times something. So we'll see that the pulse is also spread in time. So the pulse width is now broader. Right, so this is the amplitude. So we can look at the power, which is just the square of.
Sir,
Yeah.
here there is a alpha term.
Sorry.
So there is a alpha term here.
Yeah.
So what is the significance here?
Yeah. So we will modify. I mean, this is a complex number. You can take a square root of the complex number. It will get another complex number. Okay.
Yeah.
And here a complex number means, again, you can split it into real and imaginary parts, right? So the real part will give you the pulse amplitude or the intensity, and then the imaginary part will give you some phase. We'll see. Yeah, so take the mod square. So you take mod square of this. Right, so what is the mod square of this?
One plus SGN of beta 2 Z by LD whole
Square
square.
of this, right? So E naught, in the denominator I have square root of 1 plus, and sine of beta 2 is either plus 1 or minus 1, so square is always 1. So I just get Z over LD square. Right, and then here you have to take again, so you have to multiply this times its conjugate. So here also you get 1 plus Z over LD square. Okay, so now you can do a comparison. So input pulse was like this, P naught e to the minus P tau square by tau naught square. I can write this as some P Z, P naught Z e to the minus tau square by tau naught square Z. Right? Into tau naught. Not here, but not here. Right? So the peak power in the pulse, P naught Z, is now, sorry, this is P naught, right? Because I get mod A naught square here. So the peak power has gone down by a factor of this 1 plus Z over LD square, right? So after propagating a distance Z equal to LD, the peak power goes down by a factor of square root of 2, right? And as it propagates longer and longer, the peak power keeps going down. And then the pulse width here, tau Z, the pulse width tau at a distance Z is given by tau naught. Then 1 plus Z over LD square root. So it's the same factor. So the peak power is going down by the same factor as the pulse width is increasing. Right? So basically, you can see that the product of PZ, P naught Z times tau Z remains the same, which is P naught tau naught. right? Basically, it's saying that if you integrate the power, so the total energy in the pulse remains the same, right? So what is happening to the pulse? So as it propagates, it's spreading in time, and the peak power is going down, and the pulse width is increasing, right? By this factor. So again, so tau at LD is square root of 2 times tau naught. So after propagating one dispersion length, the pulse width increases by a factor of square root of 2. Okay, so basically mathematically we've seen that if I launch a pulse in a dispersive medium, then as the pulse propagates, it broadens such that the total energy in the pulse remains the same, so the peak power goes down, right? And it's basically, again, what is the physical reason for this is that the pulse has a range of frequencies, and each frequency is traveling at a different speed, right? So they basically, so initially all of them start together, but as they are traveling, one of them reaches here, the other one reaches here, the other one reaches here, right? So they're spread out now in time. And that's basically due to GVD, right? Because so now the group velocity is a function of frequency. That's why this is happening. So let's look at some numbers. So this LD parameter, I've erased it, I guess. So LD, remember, was the pulse width square divided by magnitude of the dispersion, right? So you can see that it only depends on the magnitude. So it doesn't matter if it was normal or anomalous, right? It could be positive or negative. In both cases, the pulse is spreading. Okay. Of course, this is happening for an input pulse, which is so-called transform limited, right? So the input pulse was, if you remember, just e to the minus t square by tau naught square. So it was, so the amplitude was changing. If you look at the phase as a function of time, there was no phase, right? So it was a constant phase with respect to time. Only the amplitude was changing, right? So such a pulse is called a transform limited or an unchirped pulse. Okay, and if you launch such a pulse, basically it doesn't matter if it's positive or negative dispersion, right? If it's anomalous or normal dispersion, in both cases the pulse spreads. Basically, for such a transform limited pulse, all the frequencies are present together at the input, right? And as it travels through the medium, different frequencies are traveling at different speeds. Now, depending on if it's normal or anomalous, the higher frequencies travel faster or slower, right? That's the only difference. So, in one case, like the higher frequencies, or let's say the blue frequencies in the pulse will travel further, the red will travel less, right? So this will be, I think, anomalous dispersion. So beta 2 less than 0. In the beta 2 greater than 0 case, this is just opposite. So the longer or the lower frequencies travel further or faster. than the higher frequencies. But in both cases, the frequency components are getting separated, so the pulse is spread. Okay? So that's why it only depends on the magnitude, not the sign. Right. So now, of course, if you had a pulse which already had some phase profile on it, right, it was not a transform limited pulse, then you could get more complicated behavior depending on the sign. Right. So you could have, for example, a pre-chirped pulse which already has some phase, frequency dependent phase, right, which would then get modified due to this dispersive medium. But for an unchirped or transform limited pulse, both positive and negative dispersion act the same. So if you look at glass, silica, which is used to make optical fibers. So this beta 2, the GVD parameter, crosses 0 at, we plot this as a function of wavelength. At around 1.3 micron, it crosses 0. Right, at so at 1 micron, it is about 50 picosecond square per kilometer. Right, and at 1.5, it becomes anomalous. It's minus 25. But it crosses 0 at 1.3, right? So you can see that the beta 2 comes in the denominator for the dispersion length. So, for example, if you had a 0 beta 2, that means LD would be infinite, which means the pulse would travel a very, very, very long distance without spreading, right? So, some of the initial, so like at lambda about 1.3 micron, this beta 2 is very small, about 1 picosecond square per kilometer. Okay, so if you calculate this LD, so of course we have to take some pulse width, right? So if we take a typical if you take tau naught, for example, 100 femtoseconds, which is quite short. For optical communication, we usually use longer, like 10 picoseconds or longer. In this case, you will get LD to be about 10 meters. Okay? So you can see for a short pulse, like 100 femtoseconds, even though the beta 2 is very small, the dispersion length is only 10 meters, which means after 10 meters, it will become square root of 2 times its initial width. Right, so for optical communication, you don't want the pulse to spread too much, right? Because you're sending consecutive bits, and if the pulse spread too much, then the neighboring bits will start overlapping with each other, right? And basically give you errors. So you want this LD to be large. So now, if for example tau naught was not 100 femtosecond, but 10 picosecond. Right, so 100 times longer, so that will give me 10 to the 4 times in the dispersion length, right? So 10 to the 4 times this will give me now 100 kilometers, right? So a 10 picosecond pulse at 1.3 micron in an optical fiber can travel 100 kilometers without spreading. If you go to 1.5 micron, which is sort of the standard telecom wavelength nowadays. The beta 2 goes up to 25, right? So here LD would go down from 100 to 4 kilometers, right? Because beta 2 is 25 times, so this will go down by 25. Okay, so you need to do some dispersion compensation if you're traveling long distances and using sort of standard fiber at these wavelengths. Okay. And you saw how much difference the tau naught makes here, right? Because it goes as square. So an order of magnitude change in the pulse width will give me 2 orders change in LD. So as you go shorter, as you go towards shorter pulses, the dispersion becomes really strong. Right. So how do you compensate for dispersion? Basically, what one technique that people use is you just use alternate fiber lengths of positive and negative dispersion. Okay. So you have some length which has some beta 2 of a particular sign, then you have a length of fiber which has the same magnitude but opposite sign. Okay, and you cascade like this. And remember what dispersion does, right? So here we have some input pulse. So let's say it has some spectrum, right? The frequency domain. So after propagating here L1, let's say some distance L, the spectrum here is the input spectrum times this phase, right? Which goes as beta 2 times omega square times the length, right? And now we have this next section, but it has opposite sign. So now here A at 2L will be A at L multiplied by the phase due to this, which will be negative, minus, right? So for A of L, if you substitute this, you can see that the phase factors will cancel out and you will just get A of 0. Right? So whatever pulse you had here, you will recover that here. Right? Even though in the middle it's broadening. So this is one way to compensate for dispersion in long links. Right. So basically, the point is, if you want your pulses to travel a long distance without spreading in time or changing in time, then basically the main parameter is LD, which depends on the pulse width and the GVD. So you need long pulses and small GVD. Right? If you want dispersive effect to be small. Not erase that. Okay, so let's look at this in a bit more detail. We can express this as a magnitude times a phase. Okay, so just take the magnitude of this. So if I write this as some mod of A times e to the I phi, right? So then I can clearly say, okay, this is my magnitude, which gives me intensity in the pulse, and this is the phase across the pulse. So mod of is you take the magnitude of this, which is that, right? So this we already saw. This is so this is mod is basically the square root of the power, right? Because power was mod square. So this is just the same. Right? Amplitude is going down, but you just get a square root everywhere, and we get a factor of half here. The pulse duration is increased by that amount. And this phi, the phase, is basically we have to take the argument of this is a complex number, this is also a complex number. Okay, so the real part of this thing we took it out in the amplitude, and then the imaginary part of the exponent here will come in the phase. But there is also contribution by this because this is a complex number. Right? So how do we compute this? So we want to find the phase, which is like the angle in the complex plane of the product of two complex numbers, right? So if you have two complex numbers here, Z1, Z2, the angle is basically the sum, right? So you can basically write this as the angle of this plus the angle of this. And we also know that the angle of the complex number raised to some power n is n times the angle of this, right? So here we use that property. So we have here some complex number raised to the power minus half, right? So we can write this as 1 minus I sine of beta to z over LD raised to the power minus half, right? So the argument of that will be minus half times basically we use that. Okay, so using these two formulas, I can write the angle of the phase as, so the first will be so here I have some complex number like a plus ib. The angle of that is tan inverse b by a, right? So that's that. And then here I have e to the I something. So the angle of that is basically that something, right? So I can write complex number two ways, right? Either I can write it as a plus IB, in which case the angle is tan inverse B by A, or if I write it as some R e to the I theta, then the angle is just theta, right? So this second term is of this form, so that's the angle. First term is of this form, so that's the angle is tan inverse B. Okay. So we just take the exponent here. Okay, so we get a phase, a temporal phase, right? Of course, which depends on the time or the time within the pulse. Right? We can define an instantaneous frequency, which is the derivative of this phase, right? So right, so this is basically how much the frequency deviates from my initial omega naught, right? So initially I had a pulse where basically I had some amplitude here times just e to the I omega naught t, right? So there is no temporal phase. Like if you look at the frequency here, so this is the phase in omega naught t, d phi by dt is just omega naught, constant across the pulse, right? On top of that, now I add this, right, which gives me a frequency deviation from this omega naught, which is also time dependent. So now, depending on where I look within the pulse, the frequency is different. Okay, so that's called a chirp. This is called a chirp. So a time dependent frequency is called a chirp. It comes from basically when birds chirp. If you've heard them, the sound they make, the frequency changes with time. Okay. So it goes like the frequency goes up or down. Right. So if we take derivative here, first term is independent of tau. Right. Only the second term has tau. So this will be okay. So the instantaneous frequency is linearly proportional to time. Okay. So this is a linear curve. Right. So basically, a medium with GVD imposes a linear frequency curve onto my pulse. Right. So which means what? The instantaneous frequency is changing with time. Right. So if I have the pulse here, so my input pulse is just e to the I omega naught. So the carrier is the same everywhere, right? So like within the pulse, the carrier frequency is the same, doesn't change, right? So that's my input pulse as a function of time. Or equivalently, if I want to plot the instantaneous frequency deviation from omega naught, for my input pulse it's just 0, right? So for my input pulse it's just 0, basically the x-axis. right? So that's why I'm saying the input pulse is unchirped. There's no. But due to dispersion, now there's a linear chirp, and the proportionality constant depends on the sign of the GVD. Right? So if the sign is positive, then basically you get a positive slope here. Right? So this is for beta 2 greater than 0. Right? So this is normal dispersion, and for beta 2 less than 0, anomalous dispersion, the chirp is with a negative slope. Right? So what does this mean? If I plot the pulse now, right? So the IC output, what has happened? So the envelope is broadened. So let's look at this case, normal dispersion. The frequency is increasing as a function of time within this. So tau 0 is here, right? So less than tau equal to 0, the frequency shift is negative, which means frequencies here are smaller than frequencies here, and then for tau greater than 0, the frequencies are larger, right? So basically what is happening, the frequency, the instantaneous carrier frequency is increasing, right? It looks like that. I'm of course exaggerated it quite a lot, but right, so that's how the pulse, the electric field in the pulse looks like now. So the oscillations are slower in the front of the pulse and then faster at the back, right? Which is also saying, so at the front of the pulse you have red or lower frequencies, in the back you have higher frequencies, right? So this, remember, the front, this is the back, this is tau equal to 0. So at the front, the lower frequencies are coming, which means the lower frequencies have a higher group velocity, so they come first, right? And the higher frequencies have a lower group velocity, which is the case for normal dispersion. For anomalous dispersion, this will be opposite. So this pulse will look like that. Okay. So the oscillations will become slower as you go from front to back. Okay, you can also define a chirp parameter, which is the derivative of the frequency. So basically, how does the instantaneous frequency change? Right. So for this case, since the chirp is linear, the derivative of the chirp, which is the chirp parameter, so this is denoted by c sometimes. So this will be just some constant, right? Derivative is, and that will be positive or negative depending on this. Right. So this chirp parameter c will be constant as a function of the pulse time. It will be either positive or negative depending on. So this is again for normal, beta 2 greater than 0, and this is for anomalous. Okay, so normal dispersion adds a positive chirp, anomalous dispersion adds a negative chirp. And this chirp is basically what is giving you broadening in the time domain. So is that clear?
Yes, sir.
How the pulse behave in medium with dispersion, or more specifically GVD, right? Of course, if you include higher order terms like beta 3, beta 4, then the solution is more complicated, right? So you will have other terms due to those higher order dispersive terms. Okay, so that's dispersion. So this was the case with only dispersion and no nonlinearity in the medium, right? And basically the main effect was the pulse spreads in time and acquires a chirp or a time-dependent phase across the pulse. Now we can look at the case where we just have nonlinearity. Okay, so this was the third case. So no dispersion. So let's say we are operating, let's say, close to the zero dispersion point or something, where we can neglect the dispersive term and only the nonlinear term contributes. Right. So again, if you go back to the equation, the NLSE, the first term, the dispersive term, we neglect. Only term which is remaining is the nonlinear term, right, which is the self-phase modulation here. So of course, this solution we know already, we've seen before, right? From self-phase modulation is just a phase which is intensity dependent. Right, so the pulse just acquires a phase, and this nonlinear phase depends on the pulse power. Right. So since now the pulse is, the power is a function of time, this phase is also a function of time across the pulse. Right. So if you look at the power in the pulse, that's mod square of this. That is actually invariant, right? Because you're just getting a phase in the time domain, right? So this is just so in the dispersive case, we saw that in the frequency domain, the spectrum was, so Pz of omega was equal to P0 omega, because in the frequency domain we just got a phase, right? So the power spectrum was unchanged. Here in the time domain, the power or the pulse shape is unchanged, right? Because the effect of nonlinearity is just to give a phase, temporal phase. Okay, but of course, this phase has some effect, right? The power as a function of time doesn't change, but we will see that the spectrum changes, right? In the dispersive case, the power spectrum remained the same, but the temporal shape changed. Here it's the opposite. The temporal shape is the same, but we'll see the power spectrum changes. Okay, so again we can assume some input pulse. So let's assume a Gaussian input pulse again, right? Like we did last time. Right, so that's my power, which means my nonlinear phase is gamma times P times Z. Right, so you can see the nonlinear phase also has this Gaussian shape. Okay, so this is written as Z over L NL. Right, where we define L NL equal to 1 over gamma P naught. This is the nonlinear length. Okay, just as we defined a dispersive length, here we are defining a nonlinear length. So it's inversely proportional to the peak power in the pulse. Right, so this means that this is P naught at tau equal to 0. Right, and the gamma is the effective nonlinearity in the medium. Right, so it's inversely proportional to gamma P. So you can see that the nonlinear phase goes as Z over NL, which means, right, again, so if the pulse propagates one nonlinear length in the medium, then it acquires 1 radian of nonlinear phase. Right, so the peak phase shift at tau equal to 0 is given by Z over how many nonlinear lengths you've propagated. Right, so so higher the pump power, the shorter the nonlinear length, which means you'll acquire this phase propagating a smaller length if you have more power. Again, we can define an instantaneous frequency because we have a time dependent phase, right? So again, delta omega of tau can define as minus del phi by del tau, where phi is now the nonlinear phase. Right, so this you can see becomes okay. So you take the derivative of this Gaussian with respect to time, so you get a factor of you have to use the chain rule, right? So the first derivative of Gaussian is the Gaussian, and then you take the derivative of tau square, which gives you tau. Right, so now you can see that the chirp, so in the dispersive case, we got an instantaneous frequency which was linear. Right, here we have a linear term tau, but then it's multiplied by this Gaussian term. So it's a non-linear chirp. It's not a linear chirp. Right, so if I plot this instantaneous frequency now, as a function of time across the pulse, then so near the middle of the pulse, near tau equal to 0, this Gaussian term is at its peak, so close to 1. So there it goes roughly linearly. But then out towards longer times, this Gaussian term dominates and we go back to this Gaussian kind of shape. So it looks like this. Okay, so in the dispersive case, it was only linear. Right? So if you took medium in GVD, it was only linear, either positive or negative depending on the sign. Here it looks like this, so it's roughly linear near the middle of the pulse. But then it goes to a nonlinear shape, right? And it's always positive, right? Because this nonlinear length here is always it's a positive number. So this always, it doesn't look like this anytime. It always looks like this. Whereas in the dispersive case, we saw that we could either get positive or negative, depending on the sign. So one thing you can sort of see is that, so remember with the dispersion we could have a positive or negative chirp. So if we have a positive chirp due to dispersion, then the nonlinear chirp or the chirp due to self-phase modulation will add on to that chirp, right? Both chirps will be in the same direction. But if you had the dispersive chirp in the negative direction, right? So this means with anomalous dispersion, right? Then you can see that if the magnitudes were right, then this could cancel this chirp, at least in the middle of the pulse, right? So this delta omega due to dispersion plus due to nonlinearity could cancel each other. They have different signs, right? And we could actually go back to a net zero chirp again, which means what? You go back to your input pulse, right? So you could set up a case where the dispersion and nonlinearity cancel each other out if the magnitudes are correct, right? The beta 2, because this chirp depended on the magnitude of beta 2, LD, etc. Right? And this depends on, yeah?
That will be only possible if for small tau.
Yeah, so but typically, so your pulse looks like this, right? So most of the power is in the middle of the pulse. Okay, like the power in the wings is very small, right? So for a Gaussian shape, like it falls off quite quickly. Even for other kinds of pulses like secant hyperbolic and other kinds of pulses, basically you have a function which falls off very rapidly. I mean, here we are considering Gaussian, so let's maybe stick to that. So it falls off very quickly, and the power in the wings is not much. Okay, so you're right that this is not an exact cancellation. Like at least for Gaussian, we took a Gaussian pulse shape, right? And for that, we can see that it's not an exact cancellation, right? If anything in the middle is getting cancelled, but to just give you an idea, so we'll see later for a different kind of pulse shape, specifically secant hyperbolic, you can get this cancellation to be exact, right? So if this pulse shape was different, then you can imagine both the dispersive and the nonlinear chirps will be different because these functions will be different, right? And turns out in that case, for the secant hyperbolic case, you can actually get these two to be, in that case, both will be nonlinear and it will get exactly cancelled. Okay?
Okay, sir.
But yeah, here is just to give you an idea that the nonlinear chirp is always in of one sign. Due to self-phase modulation is always in one sign, whereas the dispersive chirp can be positive or negative. So you can cancel out the self-phase modulation chirp with the dispersive chirp. Okay? It's not exact for the Gaussian. Right? Right. So basically, what is this saying? You could have a pulse, right? So now it's, let's say, traveling in a medium which has both dispersion and nonlinearity. If the dispersion was anomalous and had the right magnitude such that it cancelled out the nonlinearity, the pulse would actually propagate without any change, right? Because the chirps will cancel and the net effect will be 0. Okay, so those pulses are called solitons. We'll look at that maybe in the next class. Okay? That you could have pulses with propagate without change. So of course, the first case we saw, no dispersion or no nonlinearity, we have a pulse which propagates without change, but that's a trivial case, right? We'll see that you could also have particular cases where you have a dispersion medium with dispersion and nonlinearity. Still, you could have pulses which propagate without change. And those pulses are called solitons. We'll see more about them in the next class, but basically the idea is to cancel the chirps. Okay? Another way to look at it is if you plot the chirps, right? So we plot this parameter C, which was this chirp C, which was d divided by d tau. So if you plot for the self-phase modulation case, the chirp would look something like this. Okay, so again, basically it's a derivative of this, right? And now again, due to dispersion, you could either add a positive chirp or a negative chirp. And basically the idea is using an anomalous dispersion, if you add a negative chirp, then it can cancel out this positive chirp due to the self-phase modulation, so that the sum could be net 0 chirp. For the Gaussian, of course, it will only happen near the middle or the peak of the pulse. Okay, so yeah, so that's what happens sort of in the time domain, right? You get a chirp, the power as a function of time remains the same. You just get a temporal phase, which gives you a temporal frequency and a chirp, which is like that. So now, what happens to the spectrum? Right? So basically, our solution is for a Gaussian input pulse is this, right? To see what happens to the spectrum, you have to take, again, you have to go to the frequency domain, which means you have to take the Fourier transform, right? But actually, you can see that this is a very complicated function, right? So what we need to do is take the Fourier transform to see the spectrum. But here you can see there's e to the I some phase, but that phase itself is Gaussian. Okay, so in the dispersive case, we had the phase was sort of going linearly. We had some Gaussian amplitude times some phase, but here we have e to the I, some function which is itself a Gaussian. Okay, so it's not, at least analytically, it's not possible to just solve this. You can do it numerically. So this is complicated, right? Requires numerical solution. Can't do analytically. And then if you take mod square of this per transform, you get the power spectrum. right? And basically you can imagine, right? So we saw that basically we were getting these new frequencies, right? So these new frequencies which are being generated will give me a broadening in the power spectrum. Okay. And the more I propagate, so as my Z increases, the more I propagate, the power spectrum broadens more and more. Okay, because basically I am introducing, so this goes like this. So I am introducing more and more frequencies as Z increases. Right? So, um, so okay, again, so broadening of spectrum due to self-phase modulation. Right? So, of course, to find the exact spectrum, you have to take the Fourier transform and plot it exactly, but we can get an idea of how much the spectrum broadens by sort of finding the maximum of this again frequency chirp, right? So if we find how much the maximum of this frequency chirp, right, we can say okay, that much frequency we generate away from omega naught, right? So that much the spectrum has broadened. Right, so we had an expression for this, I erased that, right? But we had an expression for this instantaneous frequency, which was right 2ZL over NL tau over tau naught square. Right, so if we find what is the maximum frequency shift, we can say okay, that much at least the spectrum is broadened, right? So we can find the maximum of this function, right? So putting the derivative to 0. Okay, so we'll get two terms. We have product of two functions here, both are dependent on time. So we do the chain rule and two terms. So if you put that equal to 0, so this Gaussian term you can just cancel, right? And we are left with one minus 2 tau squared by tau naught square equal to 0, which means this peak occurs at tau equal to tau naught by root 2. Right? Which is saying that this peak frequency shift occurs at a time tau naught by root 2 from the center of the pulse. Right? So what is the maximum frequency shift then? It's just this delta omega at tau naught by root 2. right? So just put right. So t square by tau square by tau naught square for tau naught equal to for tau equal to tau naught by root 2 is just half. Right. So this becomes okay, and this square root of 2 over e is about 0.86. And 1 over tau naught is basically the bandwidth, right? Uh, the bandwidth of the pulse, initial pulse. Right, and this Z over NL is basically the nonlinear phase shift at tau equal to 0. Right, the nonlinear phase shift went as Z over NL e to the minus t square by tau square. So this is the peak nonlinear shift which is occurring at the center of the pulse. So basically the broadening I can sort of estimate as this constant times the maximum nonlinear phase shift in the pulse times the bandwidth of the pulse. Okay, or I can say that the fractional broadening, right? So my input bandwidth is delta omega, and then the broadening is this small delta omega. The fractional broadening is proportional to the maximum nonlinear phase shift, which is the propagation distance by the nonlinear. Okay, so how much the spectrum broadens as a fraction of my input bandwidth is just proportional to the nonlinear. Right, so this 0.86 we got was for a Gaussian pulse shape. Right, if you had some other pulse shape, this constant would be different. But it will be the fractional broadening would be proportional to the maximum, the nonlinear phase shift occurring at the peak of the pulse times some constant, which depends on the pulse shape. So the more nonlinear phase shift you have, the more self-phase modulation you have, the more broadening in the spectrum you get. Right, and if you exactly solve that Fourier transform numerically and plot the spectrum, it looks sort of like this. Let's plot and show. I'll just write it here. Okay, so we are plotting the power spectrum P as a function of omega after propagating some distance z. X is omega. Right, so my input pulse is some Gaussian pulse. So my input spectrum is also a Gaussian spectrum. Right, remember in the dispersive case we saw that the input spectrum is also Gaussian, and the width, input pulse width is, or the bandwidth is 1 over tau naught, right? The tau naught is the pulse width in time. Right, so this is my input pulse, so z equal to 0. So as you propagate, basically you acquire more and more nonlinear phase shift, which broadens the spectrum more and more. Okay, so when the nonlinear phase shift reaches pi, it sort of looks like this. Okay, so this is for phi NL max equal to z over L and L of pi. Okay, so the spectrum broadens. If you keep going further, then the spectrum shape also changes quite a bit. So, what 3 pi by 2 is. Okay, so this is for nonlinear phase shift of 3 pi by 2. Okay, so the center, at the center the power goes to 0, you will start getting these lobes. If you keep going further, then you start getting zeros at other places. So, okay, so this is for phase shift of 5 pi by 2. Okay. Now you get 2 zeros in the spectrum, but overall the spectrum keeps broadening. Okay. So basically, roughly the number of zeros in power spectrum scales as the nonlinear phase shift, the lowest integer or the highest integer lower than the nonlinear phase divided by pi. Okay, so as soon as the nonlinear phase exceeds pi, then you start getting 1 0 in the spectrum. When it exceeds 2 pi, then you start getting 2 zeros in the spectrum. But the exact shape is very complicated, right? It requires numerical solution. But in general, basically the spectrum is broadening further and further as you keep propagating. Okay, so one interpretation is like why is the pulse broadening? Of course, you can say that you're getting a time-dependent phase which is introducing new frequencies, and that is what is broadening the pulse. But physically, you can think of it as so when my pulse my spectrum has some bandwidth, right? So there is a continuous spectrum of frequencies input, right? And we saw that in a current nonlinear medium, we could have four-way mixing, right? If we have three different frequencies, we could have four-way mixing occurring, and we could get gain for some of the frequencies, right? So you can interpret that within this pulse, what can happen is like the center of the pulse has highest power, right? So that can act as the pump, right? And then the frequencies in the wings can act as signal and idler, right? So symmetrically placed about the center frequency. We can do frequencies, we can say the signal and idler, and then we can have four-way mixing, right? So omega p giving me omega s, omega I, right? And we saw that this process gives me gain for the signal and idler, right? So basically what you're doing is transferring power from the center to the wings due to the four-way mixing, right? So from the center you start transferring power to the wings, so the center goes down and the wings start having more and more power, right? So you can interpret this spectral broadening as happening due to four-way mixing within the pulse. Okay. So this spectral broadening is, of course, I mean, it could be useful, for example, generating broadband sources, but one place where it's especially useful is for pulse compression, right? So one effort is towards trying to make shorter and shorter optical pulses. So if you want to make really short pulses like less than 100 femtoseconds, then you need to go to techniques like these, where basically you need to somehow first broaden the spectrum to a very large value, and then just by Fourier transform pairs, you know that the width in time can be 1 over the bandwidth, right? So if you have a wide bandwidth, then you can get a short pulse, right? But the trick is to have to get the pulse to be transform limited without any chirp, right? So here what's happening, for example, right? We saw that in the time domain, the pulse is traveling as it is, right? Whereas in the frequency domain, the spectrum is actually broadening, right? So at first glance, you can think that it's actually violating frequency transforms, right? Fourier transforms, because if like the width in frequency has to be inverse of the width in time, then how can one increase but the other remain the same, right? Similarly, in the dispersive case, we saw that pulse was broadening in time, but in the spectrum it was the same, right? Which there also you can ask the same question, right? So what is the what is happening is actually, so that relation of inverse the bandwidth being equal to inverse temporal width is true only for a transform limited pulse, right? A pulse which has no phase across the pulse, or a constant phase, right? But we saw that both in the case of dispersion and nonlinearity, what is happening is you're introducing a chirp or a time dependent phase across the pulse, right? And that is what is giving you these effects. So, right? So you're broadening in frequency, but you're not compressing in time, because the pulse gets chirped, right? If you could remove that chirp, then it will get compressed, because you broaden the frequency, right? You broaden the spectrum. So the transform limited pulse width, which is the inverse of the bandwidth, has gone down, right? But you don't actually compress, because you have a chirp across the pulse. If you could remove that chirp, then you could actually compress it, right? So we discussed this already, right? So the nonlinear broadening introduces a chirp like this. Now, if we could follow it with an anomalous dispersion medium, which has the negative chirp, then you could remove the chirp caused by the nonlinearity, right? And now, if you basically cancel them out, then after the second, so after you first go through a nonlinear stage where you broaden the spectrum, then you go through an anomalous dispersion stage where you cancel out the chirp, which basically compresses the pulse, right? And then at the output, you are getting a pulse which is much shorter than your input pulse. Okay. So you can basically go towards shorter pulses. You can do pulse compression using this, right? So basically, what I'm saying is, the idea is, so you start with some pulse. So it has some time duration and some bandwidth, right? And so let's say you start with an transform limited unchoked pulse. So this delta omega is basically 1 over tau p. Now I send it through a nonlinear curve medium, right? Let's say the nonlinearity is much stronger than any dispersive effect, or you're operating this where the material dispersion is close to 0 or something. So now, in this stage, only the nonlinear broadening will be dominant, right? So what will happen at the output here? The pulse width in time is roughly the same, but in the frequency it has broadened a lot, right? So it has gone to some delta omega prime, which is greater than delta omega, right? This is what we just saw. Now I'm saying, so but what is happening now? So if I plot the phase, it's just constant across the pulse. That's why it's transform limited. But here the phase has some shape like that. Right? And now I'm saying, now I propagate through another medium which has anomalous dispersion, beta 2 less than 0. Right? So let's say this medium has very low nonlinearity, it has only dispersion. Right? So now I can control, for example, the magnitude or the length of this medium such that, so now it will this is not phi, this is delta omega. Sure. Right, the phi is actually the integral of this. The phi actually looks like that in this case. Anyway, so this medium now gives me a negative chirp, which can cancel, let's say, the chirp due to the nonlinear. Right. So now what has happened after this? Because I cancel out this phase, so my spectrum remains the same, right? So that's still delta omega prime in width, because through a dispersive medium the spectrum remains the same. But now I have an unchoked pulse again, which means my pulse width here, tau p prime, has to be 1 over delta omega prime. Now, since delta omega prime is bigger than delta omega, delta tau p prime is less than tau. Right, so depending on how much I broaden the spectrum, by the same factor I compress the pulse. Okay, so this technique is used in in the construction of ultra short pulse lasers. Right, if you want, so there are lasers now which can give you really short pulses, like 10 femtoseconds. So for that you need this kind of sort of compensation, right? And this anomalous dispersion medium could be like a fiber or waveguide, but it could also be just free space with like a prism pair or a grating pair. Okay? So it could be, for example, like a grating pair. Like especially for very high power lasers, typically you want to do it in free space because if you go through fiber or waveguide, you just damage it. So how do you do it in free space? Is like you have a grating pair or something, right? So then you have your pulse entering here. Now the grating will separate your high and low frequencies, right? And then you go through and retro reflect back from a mirror. So let's say this is blue and this is red. So they travel different paths, right? And when they come back, they've acquired different phases, right? Because the path length is different. So you can mimic a dispersive medium by using a prism pair, or sometimes people use a grating pair, or sometimes people use prism pairs, which does the same effect. Okay, so you have some input, the prism splits it into frequency components, and then you retro reflect back. Okay, so using grating pairs or prism pairs, you can mimic this anomalous dispersion. Right? Basically, you need a frequency dependent phase to happen. So this idea is used in ultra short pulse lasers. Okay, so we went over time, so we'll stop. So next time we'll look at when both nonlinearity and dispersion are present at the same time in the medium, and how like this cancellation can happen exactly for certain pulse shape.
Sir, can you post some paper related to construction of ultra short pulses based on this method?
Sure, yeah.
And sir, when was
Actually,
this method invented?
so I mean, ideas related to this was given the Nobel Prize I think last year or 2 years ago.
2018, I think, or
Um,
2019.
so that was called. So the technique there is called optical parametric chirp pulse amplification. Um, basically, so the idea is basically this, right? Like you broaden and chirp the pulse, and then you remove the chirp to make the pulse shorter and higher in power. Okay, so the idea was similar. They had some extra like amplifiers, etc. So I think 2019 was probably maybe well priced. Yeah. So I mean, I guess their main idea was, so what you do is first, let's say you want to amplify short pulses, right? So, but when you have short pulses, your peak power can be high. So when you amplify it, basically it can destroy your amplifier medium itself. Okay. So then how do you amplify like ultra short pulses? So their idea was, okay, what you do is first you send it through a dispersive medium, which would spread the pulse in time, right? Which would lower its peak power and spread it in time. And now you amplify it because now the peak power is low. Okay. So now it won't destroy the amplifier. And now once it comes out of the amplifier, you do dispersion compensation and compress it back again. So